Okay, so the big idea is that we know that photons have momentum and that electrons also have a wavelength. And this wave nature of matter is the reason you have quantization and the reason it's required. So you remember from a string that strings can have a case for standing waves. Then the frequency to generate a wave, to have this condition of a standing wave, is that the wavelength of the wave, in this case that's one wavelength, we have, in order for this situation to occur, we need one wavelength, two wavelengths, three wavelengths. Three wavelengths need to equal the length of this string. So lambda is going to be equal to L over 3. So that's the wavelength of this sound wave here. And then C equals lambda F for the speed of light, for example, but that's true for any velocity. V equals lambda F. So then V equals L over 3F, and the frequency then, frequency that you need to vibrate this string at is going to be 3V over L. And V would be the velocity that a wave travels on that string, which would be a function of its tension and some other things there. So this is the idea that if you're trying to create a standing wave, there's certain frequencies that work, and only certain frequencies. So not any frequency, only certain discrete frequencies. And the idea with the electron is, in order to fit an electron at this radius of orbit, it needs to have 1, 2, and 3 wavelengths there. And so then you say, okay, the circumference is 2 pi r, and it's got to have either 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, whatever, some number of wavelengths there. And then so we're trying to figure out then the quantization of an electron orbit, and then you can say, well, the angular momentum of this electron needs to be this specific case, and so on. And Bohr was the first one who hypothesized a rule for the allowed orbits, and then that quantization, n equals 1, 2, 3, or 4, gives you this quantum mechanical aspect of this, where the things have to be quantized. So the problem with the initial treatment here is it's a little bit simplistic, because it doesn't explain what's called the Zeeman effect, which is when you look at emission lines from a gas, and they're all different colors, not two pink lines, and if you apply a magnetic field, it actually causes the line to split into separate colors that are really close, and that's called the Zeeman effect. And that's a weird effect, and everybody's like, come on, I thought we had this figured out. Well, it turns out that if you've got an electron orbiting an atom, the electron can be pointed straight up, it could be pointed this way, it could be pointed that way, pointed this way, pointed this way. Whatever way it's pointing will actually change the momentum and energy that it has, which changes the amount of energy it emits when a photon when it relaxes from an energy level to another one. And so that means it's going to emit sometimes. Some of these electrons will have a little bit more energy, some will have a little bit less, based on that magnetic field and its rotation, and so you get this splitting effect. So you have to think about the electron as having momentum as it goes around the orbit of the electron, and this external field, if it's aligned this way, if the angular momentum of the electron is off at any of these other angles, then what you really care about is the component of the so this here is the component of the orbital momentum. Here it is again, but it's shorter now, and here it is, there's no component, so it feels no force. This component is a negative component, and so on. So depending on the orientation of the electron, which could be here, could be here, could be here, could be there, could be there, depending on the orientation of it, you're going to get different effects from the angular momentum. And continue on, blah, blah, blah. So these are different degrees of freedom for the electron. So the quantum numbers that an electron can have then change depending on, or don't change, but there's 4 quantum numbers you got to care about for the electron. The principal quantum number defines all of the energy levels we've been talking about up to this point for the hydrogen atom, n equals 1, 2, 3, 4, and 5, and so on. But now the angular momentum of an electron needs to be considered, where L, the total angular momentum, is going to be L times the square root of L plus 1 times h bar, and h bar is outside the square root. But L, this number, can run from 0 to n minus 1. So let's say the n equals 3 state is what you're looking at. You're trying to understand all the different possible energy levels from there. Well, you can have 0, 1, and 2 for L at that state, because it can go up to n minus 1, which would be 3 minus 1, which is 2. So L is your possible values for your angular momentum, which means it can either be here, here, or here. So you can have 0, 1, or 2. Or that one. 0, 1, or 2. Okay, and then the components of that 0, 1, or 2 could be there, which is 0, there, or there, which is going to be shown here, what we call m sub L. And it's the component that's along the magnetic field axis, which is from minus L to plus L. So if we're in the n equals 3 state, L can be 0, 1, or 2. M sub L can be 2, 1, 0, or minus 1. So then M sub L can be minus 2, minus 1, 0, 1, or 2. So those are your possibilities for M sub L. So now we've got a bunch of different degrees of freedom that the electron can take on during its orbit. Then there's finally spin m sub s, which can always be plus a half or minus a half. Okay, so your final electron in the n equals 3 state could have an L of 2, an m sub L of minus 1, and a spin of plus half. Or it could be 3, 1, 1, and minus a half. Or it could be 3, 0, 0, and plus a half, or 0, 0, minus a half. So those are all the possible states that an electron can be in around an atom. And continuing on here. So here's your quantum numbers written out again. You could have n equals 1, 2, 3, 4, so on. L can be 0 to n minus 1. M sub L can run from minus L to plus L. Electrons always have a spin of a half, which means they can either be spin up or spin down. And those are the degrees of freedom that an electron can have that give you that Zeeman effect splitting. These are all the different electron configurations. It looks like, I don't know how they project these, but some axes of projection. So you could have 1 and 0 here. You could have 2, 0, 0. You could have 2, 1, 0. You could have 2, 1, 1, or 2, 1, minus 1. You could have 3, 1, plus or minus 1. You could have 3, 0, 0, and so on. So all these correspond to the different orientations and properties of electrons orbiting the atom of hydrogen. So these are these are probability density functions showing you where the most likely electron will be around an atom. That's what those pictures are. The Pauli exclusion principle says that for every one of these states, only one electron can be in each state at a time. So once you get a 2, a 1, a minus 1, and a plus a half electron in there, that's it. Only one electron is allowed in that one energy state. Okay, that's known as the Pauli exclusion principle. There he is, and he's, actually a superhero of some kind. Okay, so anyway, so here you go. Once you start filling out your states, for the n equals 2 states, bling bling, you could have your spin up, spin down. You've got all your different values that you can put in according to the quantum numbers. So the way this works is if n equals 1, if L equals 0, you've got an S there. If L equals 1, you've got a P. If L equals 2, you got a D. If L equals 3, you've got an F. If L equals 4, you got a G, and so on. And so, for example, this shell, n equals 2, L equals 0, so that's going to be, and then you've got 2 electrons in this possible state. So this is the 2, and since L equals 0, this is the 2s state, and there's 2 electrons because it can be plus half or minus a half in that shell. The next one, we've got 2, and then L equals 1, so all of these are 2p states. So all of these are 2p states, and then there's 1, 2, 3, 4, 5, 6 possible electrons. 1, 2, 3, 4, 5, 6. So 6 possible electrons in the n equals 2 state, plus the 2 in the n equals well, the total n equal 2 states gives you 6 plus 2 gives you 8 electrons together. So this is called spectroscopic notation, which is replacing writing this table out all the time with 2s2. So this would 2s2, 2p6 would tell you this full configuration of the electron shells. And that's because once you occupy this state, the next one is occupied, the next one is occupied, the next one is occupied. You just keep going up down the line. Okay, so here you go. As you start going to z equals higher to more complicated states, once you get the 1s2 filled, everything uses that, so you don't have to keep repeating it. You have the 1s2, 2s1. Lithium is 3 protons, which is also corresponds to 3 electrons. So lithium's atomic number is 3. So you got 2 plus 1 is 3. Now for beryllium, you have the same 1s2, 2s state, but now you can have both shells filled with electrons. So now you have 1s2, 2s2, and 2 plus 2 is 4. So that gives you the 4 state. And then 1 plus 2 plus 2, so it's 2, 4, 5, 2, 4, 6, 2, 4, 6, 7, 2, 4, 8, 2, 4, 9, 2, 4, 10, and so on. And so you just keep filling this out according to this table, and this is called spectroscopic notation. So when you go to figure out what it is for uranium, what you do is you copy everything down for all the previous things and just keep extending it until you get to the full periodic table of elements. Okay, so that's how that works. See you guys later. Bye.